So if you didn't get through that packet all the way, hopefully this fills in a few holes as well. One type of solid that wasn't mentioned in your packet are ones that are not in a nice, neat structure. They'd be called amorphous. Typically, that's what my second bullet point goes over. When you cool, going from a liquid to a solid too quickly, you don't allow for a nice, neat rearrangement. And if you cool things too fast, sometimes they do not get a nice stacking structure. I actually showed you with styrofoam balls last unit a stacking structure that was nice and neat. You know, your simple cubic, your body centered, stuff like that. Amorphous solids don't have that nice, neat structure. Now this is probably less likely going to be brought up than other things because I did not see it directly on the goals, but year after year textbooks bring up different types of ways solids can form. So usually you start off with the ones that don't have a nice, neat structure, and now let's talk about things that do have structure within them. And I think my next slide I'm going to skip altogether because this is all stuff that we talked about, these different types of stacking that you really don't have to be aware of too much more. So what our focus last class in the beginning of today is on those four main types of solids and how their melting point and how hard they are and other properties can be based upon these things. So I have 4 slides left because it's the 4 types of solids that were in that packet last time. So my hope is between the packet and notes, we can do identification. Because that's mainly what we're going to be doing when it comes to these 4 types of solids. There isn't a lot beyond just identification of what are the characteristics of these things. I know some people, when I was walking around at the end of the hour last time, I tried to get you guys to get to page 5 of that packet because they had a nice big table that gave a lot of characteristics. And I kind of told people this lends itself to multiple choice. You could be given a list of properties and say, which of the following types of solids this is? So for example, ionic. We should be comfortable with ionic. If not, come in and get a little extra assistance, or let's talk through what it means to be ionic. But remember, you have positive and negative ions interacting with one another, holding each other together. It's not a true bond, it's more of opposites attract, but it's composed of charged particles. Typically, the anions and cations are not of the same size. One is bigger than the other is very common. My third bullet point, getting a little bit more into the properties. To conduct electricity means you need a flow of electrons from point A to point B. A current needs to go from point A to point B. An ionic compound in a solid form is kind of stuck in a rigid, here's my cation, here's my anion. Just imagine how we're sitting right now. If Caitlin is the cation, then Logan and Josie would be the anion. Oh, right behind Logan is Davina, so she would then have to be back to being a cation. So we're stuck in a spot. So ionic solids can't carry a current from point A to point B because they're stuck. However, if you melted it, you turned it into a liquid. Remember, liquids have a flow. They're not in a rigid structure. Now you already have charged particles, as the first bullet point suggests, and they're flowing. Yeah, you can now conduct electricity. I had to give a little lecture to, which one of you two was it? Emma, I believe, right? About the benefits of recycling and how if you don't recycle aluminum cans, the only way we get aluminum is by digging the ore out of the ground. And if you remember on our test, I had questions about an iron ore, so iron bonded to something else. Aluminum's the same way. You don't dig up pure aluminum from the ground. It's bonded with something else. The only way to get aluminum not bonded with that other thing is to melt it, and then you supply an electric current. And it's going to be something called electrolysis that we do go over at the end of the year. So you can't just do electrolysis to the solid thing. You have to do it to the liquid version because it can't conduct electricity otherwise. And then by doing that, the aluminum goes to one end, whatever the other components, the non-metal of that ionic compound goes to the other. But it takes a lot of energy to melt it in the first place because it's an ionic compound. So had to explain how it's actually cheaper to recycle aluminum, and it's easier on the environment too. But I mean, that's why aluminum's been recycled for years. It's because it's less expensive than digging things up and melting it down. Now, dissolving in water also works. So again, once you dissolve in water, these ions are floating around. They can carry a current from point A to point B. Again, in our electrolysis lab, we will be having dissolved ionic compounds in water, and we're going to be zapping with electricity, and it's a pretty fun lab that we do now at the end of the year. Very last bullet point, remember that idea of lattice energy. And Coulombic attraction we brought up last unit as well. So the idea that smaller, higher charged ions are more tightly held together, even a higher melting point. Because there's a fairly good range in melting point for ionics, but overall ionics have a pretty high melting point. Okay? To me, that one we should hopefully be a little bit more comfortable with. The electricity part I understand if we're not as much because we don't deal a lot with electricity. Molecular solids is what we went over with intermolecular forces last time. Remember this idea of intermolecular forces, van der Waals forces, London dispersion, dipole-dipole, hydrogen bonding. What holds one molecule to another molecule? And even water with hydrogen bonding, it can only last as a liquid until 100 degrees, let alone solid, which is 0, but some things can be higher than that. So that's my second bullet point is if we are looking for something that has the lowest melting or boiling points of these 4 types of bonds, I guess it'd be melting point for solids. No doubt it'd be molecular is the weakest, because that's an intermolecular force holding it together. Since these are nonmetals, nonmetals are not good at conducting heat or electricity. Again, you need that flow of current to be a good conductor. There are exceptions to that with the metalloids, but silicone has to be with something else in order to be a good conductor. Now, in the examples I give 2 examples at the very end that might look a little obscure to you, P4 and S8. You've been taught about diatomic elements, H2, O2, N2, so on and so forth. There are some nonmetals that phosphorus on its own typically exists in a 4-atom molecule. And then one phosphorus 4-atom molecule is attracted to a second one through dispersion forces. Sulfur is the same thing. So I simply put these last 2 examples on there for recognition's sake. That if you ever were to see that some other time, you would be freaked out of, oh my God, how is there such thing as an S8? That is actually how sulfur naturally is found. It's found as a molecule of S8. So again, these first 2, hopefully a little bit more review, because ionic, hopefully we're comfortable with from last unit. Intermolecular forces is what holds molecules together with these 3. So that's why molecular ones hopefully are a little more familiar as well. The one that's the hardest for people to kind of tell the difference between is the covalent ones. Because it's still nonmetals, just like molecular solids are nonmetals. But covalent is when you typically have individual nonmetal atoms that are covalently bonded together. Again, the best example that both our textbook and that packet last time will go over is the 2 different types of carbon. There's actually more than 2 types of carbon, but diamond and graphite are the 2 most common types of carbon. So now this is more an individual atom of a nonmetal, although the POGO packet gave one example of a compound, which was a little unusual. If they are covalently bonded together, they have a high melting point. In order to heat something enough to break a covalent bond, it takes a lot of energy. But since it is nonmetals, they are not good conductors. And unlike the molecular solids, we would consider these to be harder. Again, there's other properties that I could list on here. At the same time, you have that packet that shows you a lot of these. And covalent things are not going to be dissolved in water. If that were, every time my wife took a shower, her ring would disintegrate a little bit, the diamond part, and that wouldn't be good. That ring was too expensive. So it's just since I got it when I was still in college. I had to lock her down, you know. When you find someone that you know is out of your league, you lock that down as quick as you can.
She's being smart.
Exactly. Now look at me. I live in Wanakee. It's not because of me. So I didn't mention that one, but in the previous one, molecular solids, well, if it's polar, it can dissolve in water. If it's non-polar, it doesn't dissolve very well in water unless it's that very weak induced dipole attraction that I mentioned last time. Metallic. I feel that we've gone over metallic bonding already this year as well when we talked about delocalized electrons. That idea that the electrons can flow throughout the solid. It's a little bit more like you and your desk right now and passing notes back and forth. Yeah, Logan, I see you do that a lot. That's the delocalized electrons that are bouncing around between the positive cations. Because you have that flow of electrons, metallics are great at conducting electricity. Copper is one of the best at it. That's why copper wiring is used in things. Okay, when you conduct heat, that means you heat up one side of it, the other side is eventually going to get hot. Because of that flow that's allowed. And, I mean, if you melted the metallic, it would still be able to conduct electricity too. And we talked about different types of metals. We talked about alloys in the last unit as well. So again, we're starting to get to the point where the content from one topic from the College Board is overlapping with another. And that's where we're starting to get into true AP chemistry, where it's no longer just learn this, learn that. Learn this and remember that is what we have to start being able to realize. So I'm hoping as we go over things, and this is the last slide, by the way, I'm hoping as we go over things, you start to make those connections. You start to reflect back on what we've done, and then hopefully recognize, oh, that means this or that means that. Because that's the level where we need to get at here. So again, the goal sheet you picked up on the way in was titled Solids, Liquids, Gases, and if you read that, again, solids are kind of in a more or less fixed position, but there's some movement like you guys are right now. Liquids have a flow, but they're still stuck together. Gases all over the place. I'm hoping this looks familiar to you from Chem 1. This was a heating and cooling curve that we talked about with states of matter, and I just like this depiction because it shows that kind of structure of a solid, but not as much for a liquid, and gases are all over the place. It reminds you of phase changes that occur as well when you go from a solid to a liquid or a liquid to a gas, and then vice versa. Now, this graph only deals with temperature. However, we introduced to you in Chem 1 things like heat of fusion, which would be the melting energy, heat of vaporization, to go from a liquid to a gas, heat capacity, how much energy is to heat up a liquid, but you can also have a heat capacity for a gas or for a solid. Now, what I have read about the goal units for this unit here, none of that math that we did with this is included in that. Therefore, your unit test does not have that. That causes me to pause a little bit, however, because I have seen that type of math on the AP exam. I think 3 years ago, they had a free response where you had to do like 2 steps. So today in notes, I am going to go over one example of how to do that math. However, it's not on the website, and I do not plan on having it on a unit test. So I'm curious if second semester, when we have a unit that's a little more focused on energy, if we're going to bring up phase change energy again. I don't think it hurts just to see it now and then see it again, especially for seniors who haven't seen it in over a year anyways. But rest assured, that part is not actually on your test. When we have those plateaus, we refer to it kind of being an equilibrium state between both a solid and a liquid. Again, that's when 2 states of matter can coexist on those plateaus. Like I mentioned before, in that solid to liquid plateau, the heat of fusion is what's referring to the energy needed to turn that from a solid to a liquid. I believe even on the POGL packet last time for Texas solids, it referenced heat of fusion. Because again, if there's more energy required to break it apart, it must be held together really tight. Again, remember my last point here with terms endothermic and exothermic, things that we talked about in Chem 1. Endothermic means you're putting energy in. Exothermic energy is being released. Again, we dabble a little bit with energy these first few units. Lattice energy was brought up as well. Again, those graphs for potential energy with the dip for the bonds. Second semester is when we dive deeper into energy. Liquid to gas, that would be referred to as heated vaporization. Again, the symbol would be that right there. Recall that when you go from a liquid to a gas, you are now having no more intermolecular forces at all because the molecules are typically moving too fast. Okay, think about when you go from a liquid to a gas, you are heating things up. Molecules are moving faster. Solid to a liquid, there's still attraction. It's just not rigid structure. So we don't completely break intermolecular forces there. Heat of vaporization values are typically larger than heat of fusion values because it takes more energy to completely break all attractive forces rather than just loosen it up a little bit. So sometimes you could compare those two numerical values as well, which is what I'm kind of referring to as this last bullet point here. It's a much larger number than heat of fusion. Okay. Boiling. I'll get everything on here. You just did a reading guide dealing with surface tension. You're going to, in a little bit, do a reading guide dealing with vapor pressure. I was canning last night. This is what I do. I do work. I make apple butter and applesauce and apple pies as well. So last night was apple butter. Have you ever had apple butter, Maggie?
I've not.
Oh, it's delicious. It's just really potent apple, and you just spread it. You know, like peanut butter. So in the canning process, you got to boil water. You have to put your stuff inside of it, and you know, water's boiling all over the place. The bubbles always start at the bottom and work their way up, and that's to deal with density. But again, the bubble itself, this picture is showing the bubble. There's gas inside there. That's water vapor. So it has a pressure pushing out. But then there's water molecules surrounding that bubble that are pushing back in. And that's what's holding it as a bubble structure. Now, eventually that bubble comes to the top, and then it releases. However, that release, where that bubble comes to the top and then goes out, is dependent upon air pressure pushing down on the surface of that liquid. And that's where my two water examples here are. We say that water boils at 100 degrees Celsius, but that's because at sea level, which is 1 atmosphere of pressure, that's how much is pushing down on the surface of that liquid. That's when it would happen. Mount Everest, on the other hand, a lot higher than sea level. Higher elevation is a lower pressure. If there's less pressure pushing on the surface of that liquid, the bubbles are going to escape easier. It's going to boil faster. I think I'll try to find you an example maybe next time. I have a enormous syringe that I can get water to boil in at like 60 degrees Celsius if I pull out the plunger to decrease the pressure. Because at that point, then it'll start to be just like Mount Everest. So typically we think of boiling as that process, you know, when you create the bubbles. But really to boil, that vapor pressure needs to be with that outside pressure. Because if there's a greater pressure pushing down on the surface of that liquid, that pressure, then that surface tension would prevent that bubble from rising and escaping as easily. So just another way to think about phase change is we need to think about how it's not just temperature that affects it. Now my next page here is trying to make that connection between phase change and intermolecular forces. So again, I give you 3 examples here. CH4 is methane. That's the gas that comes out of our natural gas jets. C6H6 is benzene. Remember that ring that we talked about that's a resonance structure? And then water. And their primary intermolecular force, again, carbon-hydrogen bonds are nonpolar, so that would have to be a dispersion force for those first two. Water, however, its primary intermolecular force is hydrogen bonding. Heat of vaporization, how much energy per mole is required to make that liquid go into a gas? Water with a greater attraction requires more energy. And that's hopefully one of the things that we're seeing here. That connection between intermolecular forces from last time, because we have to be able to identify that, and then behavior today. Notice how benzene has a higher kilojoules per mole than the methane. Larger nonpolars have more dispersion forces in order to hold them together. And then the last column, boiling point, will show the exact same type thing. Again, I warn you that there could be some nonpolars that actually would exceed water's boiling point, but they'd have to be massive. They'd have to be really big nonpolars. Now, just as I've been talking, I thought to myself, you know what? No, I don't want to go over this today with you because it's not a requirement, so why should we visit this? I'm just going to remind you of a little bit of what we would do in Chem 1, where you would have a problem like this. How many kilojoules of energy is needed to bring 45 grams of ice at -5 degrees Celsius to 105 degrees Celsius? It'd give you the heat capacity of water, which, by the way, the heat capacity of water is pretty high. Not many things are able to absorb energy before their temperature changes as well as water does. Remember what you'd have to do sometimes is you'd have to do like a Q equals MC delta T for each state of matter. Does that equation look a little familiar to you? I believe that equation is on our equation sheet, but again, we'll be going over more of that later in the year. And sometimes you'd have to do Q equals mass times the heat of fusion or the heat of vaporization, depending upon what phase change you were doing. In Chem 1, I did not give you these values as kilojoules per mole. I gave them to you as joules per gram. So I did a couple of conversions for the Chem 1 students when I reported those numbers. That way they didn't have to convert their grams into moles, and it made life a little bit easier for them. Typically, heat of fusions and heat of vaporizations are given in kilojoules per mole, so that requires AP students a little bit more work to do in order to solve those. But again, I'm not going to go over that entire problem right now because you're not going to see that assessed this semester. Here's our last slide. And here's the thing that on your goal sheet says prior knowledge. I'm trying to convince chemistry teachers to do this year in Chem 1 as well. Showing you that state of matter is not only based upon temperature and intermolecular forces. Because really, that's what we do in Chem 1. We say, hey, hotter it is, the more likely it's a gas. Sure, but also how well is it held together with intermolecular forces? We got to realize y-axis pressure plays a role in this as well. Because if you squeeze things closer together, supply a higher pressure, as means you go up higher on the y-axis, if you put molecules closer together, they're more likely to attract to one another to be a solid or a liquid. Lower pressure means the molecules have a lot of space. Notice how gases are present even at really low temperatures on this graph. And that's because when it's low pressure, they're not close together. How can they attract to one another to be a liquid or a solid if they can't be close to one another? As you increase the temperature on the x-axis, yeah, gases are more likely. Because if molecules speed up, it's harder for them to attract to one another because they're moving too fast. Notice in the graph in the middle, there's what's called a triple point. There is the perfect temperature and pressure for different substances, and it's different for each thing based upon intermolecular forces, where all three states of matter can coexist. Not just two like on our heating cooling curves, but all three can. So that's what the triple point is referred to as. When I look at these two graphs, it looks like the graph on the left is the one for water. The way I know that is at 1 atmosphere of pressure, the normal boiling point, NBP, is 100 degrees Celsius. The normal melting point is 0 degrees Celsius. Water is also a little unusual in that it's actually more dense as a liquid than a solid. And I can tell that by, as the pressure increases, this is actually getting more liquid. Most things are more similar to this graph on the right. And that one might be for carbon dioxide. Where, again, you have a triple point, but then you also are going to have more solid present as you increase pressure. This critical point that's brought up to you on the very top right hand of each graph is just referring to, at some point, you have heated up that substance so much, those particles are moving so fast, I don't care how much you squeeze them together. They can't attract to one another. They're not going to be able to be a liquid at that point. So that critical point is usually the last point where it could possibly be a liquid. After that, it's just going too fast. So when we talk about phases, again, you can look at that goal sheet. It's going to break it down into, again, how are the particles structured? But then what you guys should be able to do is identify there's really three factors to determine state of matter. The temperature plays a role in it. You've been taught that since middle school. You heat things up, they're more likely to melt and more likely to boil. Pressure plays a role in it. That's what I'm kind of going over today. That when you squeeze things closer together, they're more likely to be a solid or a liquid because they can attract to another. And that third point, then, that attraction is the intermolecular forces. So we need to be comfortable with all three versions of this. Now, what I can tell you is that this type of graph, I think you should expect to see in an assessment I would give. I know it's going to be on WebAssign tonight as well. Because we didn't cover it in Chem 1, so even though our goal sheet says, hey, don't worry about it because it's prior knowledge, it's not prior knowledge for you guys because in Wanakee we haven't taught this graph before. So I want you to be aware of that as well.